Yeah. It's like focusing on the hypothesis and the importance of developing the hypothesis, and then deducing the rest of the findings from the hypothesis, and as opposed to getting the facts first and then coming up with the theory or hypothesis.
All right, that sounds a little bit fuzzy, but we're going to talk about that some more today. So we'll clarify, right? Any little shadiness that we have, we'll have that clarified. But yes, but he did propose that instead, what we should be looking at is what he calls the hypothetical deductive approach, all right? Which is the same as falsification, which we're going to look at in the latter part of today, as soon as we get through some of the other things that we want to do. All right, so any questions at this point before we move on? No. All right. Okay, so I also asked you to read the article, Revisiting Is the Scientific Paper Fraud by Howitt and Wilson. I hope you had a chance to read that. I have a couple of questions. What conclusions do the authors draw? Based on what you have read, what conclusion did Howitt and Wilson come to in their paper, Revisiting Is the Scientific Paper Fraud?
I guess they kind of agreed with Medawar, and they didn't believe that anything had changed, like in the sense since Medawar wrote his paper, they don't believe that the way that science is presented to people has changed very much.
Okay, yeah, very good. So that's pretty much the conclusion that they have come to. Did we look at when this article was written? Yeah, Jason.
2014.
Right, so this one was written in 2014. Medawar did his in 1963-64. So we're talking about 50 years later. And they're saying 50 years later, nothing much has changed, which is like huge, right? So we're still pretty much presenting science in a very inductive way, presenting the process of science in a very inductive way, in this very straightforward linear manner. So nothing much has changed. So probably you begin to ask yourself, so if we do this again in 100 years, will anything have changed? But yeah, that's just something to think about. All right. Okay, great. All right, so let's look at what we're going to be doing today. All right, and move on. All right, everybody can see my screen? Can everyone?
Yes.
Oh,
Yes.
okay, good.
Yeah.
All right, thanks, guys. All right, so we're continuing. We had started with induction. We're still going to talk a little bit more about induction. But by the end of today, which is when we hope to finish, when we hope to finish this unit, we want to be able to add some more to it. So at this point in time, we're able to explain the theory of induction, and we also looked at a couple of arguments against induction. We're going to look at some more that have been put forward. We want to see if there are any arguments for induction, and we want to provide some examples of induction, the use of induction in science, if there are any that we can come to. We also want to talk about falsification and provide at least one example of the use of falsification in science teaching. All right, so that's our work for today. So let's see. All right, so I want us to consider two scenarios, just to kind of use what we have talked about before. So consider scenario A, and then I'm going to move on to scenario B. All right, so I want you to read that and process it. So I'm going to give you like 2-3 minutes to do that. And then I'm going to show you scenario B, and then we're going to consider them. So in reading both scenarios, what I want you to consider is this inductive or is it not? Right? So let me give you 3 minutes for that. All right, are you ready for the next one?
Yes.
Okay. All right. Okay, so let us consider now which is inductive, if any. Your time.
Ashley from Bermuda.
Yes, Ashley, please go ahead.
I would say that the first was inductive and the second not.
All right. Okay. Can you support your reason for choosing the first one as being inductive? Let's go back and look at it. All right. Yes. Go ahead and tell us why you think.
There's some clear examples which they. Let me see. Hold on. I was just reading.
Yeah.
Basically because they used specific things like the litmus paper, and they tested it over a variety of times. Those were reasons why I chose it as inductive, but I can't find it in the reading. I was just reading chapter on introducing falsification, and I can't find where exactly it's had a good synopsis of why A would be inductive.
Oh, you're probably reading the wrong chapter. You just said you're reading one on falsification.
Oh, right.
Yeah.
Chapter 4.
Right.
Let me see. Okay, well, I'll pause my mic and find it.
All right, no problem. You can always come back and share. All right.
Okay.
So anybody else? Yes.
Yeah.
Yes, Andrew. No, that's Ava.
Yes, it is.
Yes, go ahead, Ava.
I said the first scenario was no, it was not inductive, but the second was.
All right. Why?
And you're going to ask me why, I know.
Yes.
Because it stated the teacher actually told the children that acid turns blue and litmus paper red, and she told them actually the results. She did not let them discover what the results would be. They did not do any observation or the experiment. Before they actually knew what was the acid or a base, she told them the results. And the next one, the second scenario, she just tell them that these are acid and bases, and then based on the observation, then you would have found out. You would have say, okay, I use hydrochloric acid, and that one turned whatever. So they will have to make their own inferences based on what they did. Because you said that inductive process, it starts with simple, it's unbiased, it's unprejudiced, naive and innocent observation, and then they move to facts and generalization. That's what I based that my little synopsis on.
Okay, thanks, Ava. I'm going to let's go around and then we'll discuss and say what is correct. Okay. All right. So who else wants to speak on it? A and B? What do you think?
Yeah, just a comment. Oh, sorry. Go ahead.
I think it's the first one is induction and the second one is deduction. I think the first one is induction because you've given two facts. Acid turns blue litmus red, and a base turns red litmus blue. So there's the two facts leading to a theory, and then I think in B they use that theory and then go and test their substances.
All right. All right, thanks, Tracy. Go ahead, Jason.
Okay, I agree with Ava. The first one is actually deductive, and the second one is inductive. And I wouldn't say that in scenario A that the teacher gives them the results per se, because they still have to determine which one is acid or base. But what the teacher does is give them a general concept first, which is that acids turn blue litmus red and bases turn red litmus blue or whatever. That's a general concept, and then they're moving from that general concept to the specific details about each chemical that they're going to test. Whereas in scenario B, it's the opposite. They're given specifics like which one is acid or base, and then they have to infer the generalization.
Okay.
So that's inductive, going from specific to general.
Thanks, Jason. All right. Who else is there? Linton? Linton.
Yes, I'm there.
Hi, how are you?
Okay, I'm good. Sorry for being late.
That's all right. All right, you
Today's
want to?
graduation at our school, and I had to help the teachers with the groundwork.
Oh, that's okay, Linton. No problem. We're glad you're here.
Thank you.
Did you see the scenarios? You got a chance to think about the scenarios?
Yes, I was following it.
Okay. All right. So, do you think either is inductive or not?
Well, from reading the two, I see the first one, the first scenario, has been deductive.
Okay.
Scenario B has been inductive.
You said B is inductive. You think B is inductive?
Yes.
Okay. All right. Thanks. This is all right. Let's go around a little bit more. Who else would like to share? Anybody else? Before we.
I agree with Eva and Jason that the first one is deductive, because saying that acids turn litmus red or bases turns litmus blue is general, and then going to specific substances being acid or bases.
Okay.
But scenario B, for the life of me, I still disagree. I don't see scenario B as being inductive. I still think it's deductive.
Okay. All right. Why?
The teacher has told them that some of these are acids and some are bases. And then by testing, the students are going to determine which specific substance is an acid or a base. So I still think it's deductive.
Okay. All right. All right. So let's continue the discussion then. All right. So let's go back to A. And let's just look at it. All right, so most persons tend to think that this one, because I have recorded the votes, that A is deductive in nature, and I agree with that analysis. All right, so let us look at why. So we start off, we said the teacher tells the students that acids turn red litmus blue. Yeah, red litmus blue, blue litmus red, sorry, and bases turn red litmus blue. So what we're starting off with generalization. So those are generalizations. All right, so that's the first thing that we would have to see, that those are general statements, and then from using those general statements, students are now going to carry out an activity, and they're going to carry out an activity to determine whether some substances are acids or bases. So therefore, what they will be doing, they'll react each substance with the litmus, and then they will see. So they may have, so they'll have their general statements: acid turn blue litmus red, and bases turn red litmus blue. That's their general statement. Then they will react it with a substance. Let's just call it substance A, and it will say substance A turns blue litmus red. So if they get that result, then the conclusion that they would come to, the logical conclusion, would be that substance A is therefore an acid, right? So yes, we are going from general to specific. So that is deductive, right? So that's correct. All right, so kudos for everyone. All right, for scenario B, all right, so scenario B, I think is inductive. All right, so here we are now. We have some substances. We know that some are acids and some are bases. All right, we have their names. So for example, we have hydrochloric acid and sodium hydroxide and a whole other set of stuff. And we are going to react them with litmus. So we would be able to say, for example, hydrochloric acid turns blue litmus red, sodium hydroxide turns red litmus blue, etc., etc. And we could have we'd have a whole list of specific statements. And then at the end, we would be able to look at our list, because we would then see hydrochloric acid turn blue litmus red, nitric acid turn blue litmus red, phosphoric acid turn blue litmus red. And sodium hydroxide turns red litmus blue, ammonia turns red litmus blue, etc. So from that, we would be able to generalize and say that acids turn blue litmus red, while bases turn red litmus blue. So it's actually flipping the first scenario around. So instead of now going from general to specific, in scenario B, we're going from specific statements or specific facts to a generalization. So that's inductive. So that's, yeah. So Sandra, you said you didn't see the inductive nature of it. Is it any clearer now? Because you might have been thinking in a different way, and I think I got where you were going. But do you understand from this point?
Yes, I get what you're saying. Just let me have a little time to put it in my head.
All right, no problem. All right, in the meantime, as you ponder on it for a minute or two, you can think about if you have any questions before we go on.
So you're saying that A was general because there was no specific substances that were.
Which one you're referring to now, Ashley?
Scenario A.
Right. So we said scenario A starts generally because the statement that acids turn blue litmus red while bases turn red litmus blue is a general statement. Because acids would be like a big group of substances and bases would be another big group of substances. So those are general statements, right? So we start off from general and then we find a substance and we test it with litmus and it turns it red or blue. And based on that, we say, okay, so this substance is an acid or this substance is a base.
Okay.
You clear?
Are we going to have more examples of this?
No, I didn't plan to. I just threw it in, just to cement what we had said about from general to specific versus specific to general.
Okay.
But at the end, I have some little cases that we will talk about. So then when we do that, perhaps you get some more practice in looking at what is specific versus what is specific to general versus general to specific, etc. All right, so any questions here? Any other questions, sorry? All right. Okay, let's continue then. All right, so we're still talking about induction, and there are two articles that I read for you because I thought you might have a little reading overload. So I just read them and then made note of the main point, basically summarized the article. One is an article by Michael Clapper that is entitled Beyond the Scientific Method, Should Science Be Taught as a More Creative Process? And these are the main points that Clapper makes. So let's look at them. All right, so the first point that he makes, right, is that any approach that emphasizes a particular methodology is going to run into some problems because there is no set way of doing anything, and there may be many routes to the solution of a particular problem. So when we establish an explicit set of rules, we are putting ourselves in problems. And that is what induction really, when we talk about the scientific approach, the scientific way, the scientific method, which is something that is associated with induction, then that's what we're talking about, essentially, this clear-cut path, this particular way of doing things. So Clapper is saying that approach we're going to run into that problems with that approach, because most times, if not all the time, there is more than one solution, more than one route to the solution of a problem, right? And then the other thing he says is that we have so many different situations, and each situation is unique. So the rules that will apply for one situation may not be applicable in another situation. And therefore, it's not possible to say this is the way, right? Because when you meet upon a situation that does not, where those set of rules don't apply, then what do? Right? So basically, he's making the point that we need to find another way, another approach to science teaching that does not rely on this rigidity of method, right? And this rigidity of method is, of course, in the inductive approach. So essentially, the point he's making is that he does not believe that the inductive approach to science teaching is but sufficiently represents science or represents it well. So essentially, he is arguing a similar point as Medowa argued in his article, but probably a little bit more strongly, I think, because he's not just talking about the process. No, he has gone into a little bit more about how we do science. Yeah, all right, let's take a breather. Any comment from you? Is Samuel here as yet? I'm sorry.
I thought of the comment kind of related, but about the revisiting science papers as a fraud, or the second article that we read.
Yeah.
I thought it had some good points about it. It reminded me of what Ava had said on Tuesday about, they need to organize it in some way, because they were making the points that in certain situations, science students they don't need to know about like all the errors and stuff, because they're just focusing on learning, the specific results or something like that.
Right.
So in some cases, it may be fine to have that format, as long as overall they're presenting this kind of approach that Clapper is saying as well in other situations. I guess, does that make sense? So don't outrule it completely, but just
yeah.
Does that make sense, I guess?
It made sense to me. I understand what you're saying. Yeah, we did say, that in terms of writing for particular audiences, that the inductive approach is very convenient, right? Which is a point that is made. But at the same time, we're saying writing in that particular way or presenting the science in that particular way, depending on who ends up reading what it is that is written, they could come away with misconceptions about what science is like and what the process of science is like. And therefore, I think, I'm going to get to talk about it a little bit more, that induction really does have its place, but I think it has to be more of a balance. It's not necessarily to say, okay, it has to be induction and nothing else, all right? But probably what we need to do is be able to strike a middle ground. So it has its place, so we can use it when it's appropriate. When it's not appropriate, then you use something else. Right, or present the inductive way, but also show students, if we're going to be allowing students, for example, to get familiar with journal articles, etc., while we expose them to those journal articles and the template or the format that is used in scientific field, we also want to expose them to the understanding that this is the way we write it, but this is not the process. This is not actually the way that the science is done. So a sensitization of sorts, and just help them to understand more about the science. So yeah, because I think once you have that understanding, that background, then it really doesn't matter how the paper is written, because you pretty much, you have a fuller understanding. You're more rounded. You get it.
Yeah, thank you. That makes sense.
Okay, thanks, Jason. All right, anybody else? Any other comments? Samuel, good morning.
Good morning.
We're glad to have you.
I was having problem with the internet.
Okay. All right, we're glad you're here.
Thank you.
Okay. All right. So we're going to go on now. So that's the Clapper article. We're now going to go on to look at an article which is written by Rosalind Driver. And Driver is a very prolific writer. When you begin to look at the literature on nature of science and just science research in general, you'll find that she is one of the persons who writes extensively in the field. So you can check out some of her writing. But all right, so Driver writes on the fallacy or the falsehood of induction. All right, so let's look at what she has to say about it. So, Driver notes that the empiricist view, which is the view that the common sense view that we have been talking about, you may recall. So the empiricist view that all knowledge is based on observation and that laws are arrived at from induction, etc. She's saying that this is flawed, right? This is a flawed view. It is problematic. And the reason she thinks that it is problematic is because contrary to what the inductivists believe, induction actually presupposes or assumes observations, right? Assumes theory. So essentially what she's saying is the point that we have been making over and over again, which is that all our experiences that we have and everything that happens to us, those inform, affect, have an impact on how we view things, right? So when we make an observation, that observation is really not made in isolation, but that observation is influenced by all the experiences that we have had. And so, like Medawa, Driver suggests an alternative. She's saying we need an alternative to induction because when we consider the very base of it, the base is flawed. So she proposes the hypothetical deductive method, which is also called constructivist. She also calls it constructivist, and it is also referred to as the falsification view, all right, which, as I said, we are going to be looking at. So that's a different view, right, and we'll spend a little bit of time looking at it. But let's see what else Driver says. All right, so another thing that Driver did, she did some research with students and she put forward how students made observations, but when they made those observations, the conclusions that they arrived at were actually flawed. And so the point she's making is that the reason the so-called facts that the students arrived at, the reason those facts were flawed was because students already had some preconceptions that influenced what they were seeing, what they were observing, right? And so she concludes that induction in science teaching is a fallacy because students' observations very often, probably most often, students' observations, unguided observations, will not lead to sound theory, right? And therefore, there is a need to present the theory as well in order to help students to put their observations in the proper context, right? So she's advocating for something else, that there is need for more than just induction. All right, so I'll give you a moment. All All right, so I'm not sure if by now you're asking yourself, or you haven't asked yourself like a couple of times, because basically when you read the literature, you realize that like there are tons and tons of criticisms of induction. So probably you're saying to yourself, boy, this induction seems like a really awful thing. So is there really any place for it? So let us spend a little bit of time looking at that. All right.
Okay. Can I ask a question, please?
Sure, Ava. Go ahead.
Yeah, I'm thinking. The thing is, you said cite examples on the slide. Eh? Cited examples to show how students' observation led to incorrect facts. I somehow have a problem with that. I don't know. Incorrect facts.
Yeah.
To me, I'm confused because maybe it's just English. When you said incorrect facts, I'm thinking that fact is actually what it is. Facts are supposed to be concrete, solid. You know, that's it.
Okay. All right. I get.
Once you have it as incorrect, then again, it will not be
a fact.
Yes, and then maybe I'm thinking that the fact is incorrect fact would be what I see, what I think that is it. I see that's green, that's what I see, that's a fact. But in reality, it might not be. That's what I'm thinking, maybe.
Right. So the point is, well, I understand what you're saying because you're using fact in the way that we normally use it. Right?
Yeah.
Right. So when we talk about facts, we assume that facts are true. Right?
We're supposed to know that it is.
Yeah. Right. So we couldn't have incorrect facts because that would be saying that we have untrue truths, which doesn't make sense. Right. So I understand the position that you're going from. But when the driver talks about, I probably should put it in inverted commas, but what she was saying is that the statements when the student, because remember that the common sense view is that when you make an observation, that observation is going to be the exact same thing as a fact, right? And the point driver is making is that students made observations, but those observations that they made were actually inconsistent with what we would consider to be the truth of the matter. So that is what she's calling the incorrect facts. Because remember what the examples that we use with the illusions, if we go back to that, right? That we could all be looking at the same thing, right? So visually, it's the same object that is there, but we all see it in different ways. So that would be if you you make one statement, I make a different statement, etc. Those would be the incorrect facts. So that's what she means within the context, right? Is that clearer? Do you understand what I'm saying?
Yes, I understand. I mean, I give the example. Up to now, I cannot see the old lady in the drawing that you give, the picture that you give. I kept looking in my mind. I never saw her. And then recently there was a dress online and saying what color it was. I was seeing one color. My husband was seeing another color. So I guess.
Yeah, I remember that. I remember that one too. It's supposed to be a blue dress.
Yeah, and I wasn't seeing that. So.
Okay. Well,
okay.
Yeah. Okay. All right. Any other questions here or comments?
I have a question.
Yes.
One thing is, whose phone's ringing?
Sorry, Jason.
Somebody's phone ringing or something.
Yeah. Okay. Hang on a sec. Okay. All right, we're back. Got that. That's the one. All right. So let us continue.
Oh, I also had a question though. I was wondering, so like theories, are theories scientifically provable? I mean, is that like a characteristic of a theory? Would it have to be provable by scientific methods, or not necessarily?
Not necessarily, because remember what a theory is. Theory is is a sort of generalization, a sort of explanation for a set of facts. So we have this set of facts and we come up with an explanation for why we think this is what we see, right?
Okay.
So not necessarily, and that is why we talk about the fact that these theories really should be tentative, right? Because when we talk about scientific knowledge changing over time, so if we get better information, for example, and we found out that in truth and in fact not all acids turn blue litmus red, then we would have to change our whole understanding of acids and bases, the theories surrounding it. All right, so as we get more information, or what we call more facts, right, then we would be inclined to adjust our views in line with the facts.
Okay, thanks.
All right, no problem. All right, let's proceed then. What's the matter? All right, right. So this is the question. So is it that our conclusion about induction is that it is not useful? And I'm saying induction is still useful for a number of reasons. All right, so one, let us consider that it is not possible for us to investigate all the possible cases or examples, right? Because remember that one of the criticisms of induction is that it is generalizing from a limited number, but that number is always going to be limited, because when is it going to be possible for us to investigate all cases, right? So at some point in time, we're going to have to make conclusions. We just have to understand that that conclusion is not 100%. It's not based on 100% of the sample, right? So we still have to use induction, is my view. So I say, yes, it's still useful. The other thing is that induction makes sense, right? It's practicable. We live in the real world, it makes sense, as long as we use good sampling methods. All right, so we can't sample everybody, but can we get what statisticians call a representative sample? If we use a representative sample, will that give us good data on which we can draw a conclusion? And that's the basis of statistics. The statistics, you never sample the whole population, well, for most studies, right? But what we do, you take a representative sample. When you take a representative sample, you are able to, from that representative sample, to make some general statements. So it is practical, it makes sense, and we can't investigate all cases, so let's work with some. And another argument for the usefulness of induction is that, well, there is some scientific knowledge that actually has been established by induction. So for example, the law of conservation of energy actually has arisen out of observations that energy is conserved. And so while induction may not be useful for establishing all scientific knowledge, it certainly is useful for establishing some. So there, it still has its place, a big place, dare I say. Right. Any comments? Because I still have a couple of other comments. But I want to, if anybody wants to comment. What do you think? Do you think the induction is useful based on the argument that I have brought forth, or any other that you want to bring forward? All right, very quiet. So let me so let me throw a question out here. When you think about much of the experimental work that we do today, would you consider it to be inductive or not?
Well, I know in terms of the classroom, it's heavily inductive because if you look at ecology, you go out and you take a sample and you use that sample to make some generalization. And that's what we pretty much do in all our labs.
Yeah, that is true, right? So if you begin to think about a lab in whatever field that you're in agri, in chemistry, in bio, whatever it is in science, you notice that most of the times what we do, we carry out an experiment, and from that experiment we gather our data, and then from the data we basically make some general statements or come to a conclusion. So that's inductive, right? So although there are many arguments, philosophical arguments about the base of induction is unsound, you see that induction is something that is very, very strong in science. We use it a lot, right? We use it heavily to carry out our experiments. We also use deduction, right, as in the example that I showed you. But one of the things that is happening now, deduction is considered to be a more traditional approach, right? And it's associated with what we call verification lab. And a verification lab would be a lab that you already know what the result is going to be. So basically, you're just verifying that this is the real result. So for example, suppose your teacher says, okay, today we want to demonstrate that water boils at 100 degrees Celsius. Well, you already know at the start that when you measure the boiling point of water, it's going to be 100 degrees Celsius, right? And so that's a verification lab, and that takes a deductive approach. But most of our experiments, well, I probably shouldn't say most because I don't have any data, right? But in many instances, we use the inductive approach. We gather our data and then we draw some conclusions based on the data that we have.
Another, Ashley from Bermuda.
Yes, Ashley.
Another good example of, I guess, deductive experimentation would be like quality control, quality analysis labs in manufacturing things. Mm-hmm. So say for instance, you produce bottled milk products, like, you know, chocolate flavored milk.
Okay.
So then you have to make sure everything's in spec. So you do the tests and you already know what results you're looking for. Yeah? Mm-hmm. Would that be a good example? So you're doing like different micro tests and different tests on machines using maybe a thermometer, you know, I don't know. I'm just saying, like, because you know what specific things you're looking for, that would be deductive. You know what your results you're looking for.
Well, it's a little bit, that one is a little bit shady. Okay, so you know what all right, let me use something that I understand, because I may not understand the micro test. If you're testing for like starch, let's make it very simple. Are you saying that because you know that you're looking for a blue black color, then you're saying that is deductive? Is that what you're saying?
Because you know the results.
Yeah, so I'm saying, suppose, I was just trying to simplify it. So I'm saying, if we're doing, for example, if you're carrying out the starch test on your product, and you know that you're supposed to get a blue-black color, are you saying that is deductive? is that a good analogy for what you were saying, or that's a terrible analogy?
I don't know about the analogy that you're. Yeah, I don't know what you're trying to.
All right.
Can I make a point?
Yes, Eva. I'm coming back to it. I'm coming back to Ashley.
I think I understand what Ashley's saying.
All right.
Ashley, you correct me if I'm wrong. When you in the food labs, whether you doing processing chicken or meat or whatever, let's say milk, for example, there are points at which you test your product. It's called HACCP, Hazard Analysis Critical Control Points. So the science, whoever is there, tester will just go in and test to see. They will have a point at which they will say, okay, that's fit for human consumption or not. And then they will test the microbial load at each point going through the process to say, okay, that process is fine, and they move on to the next, and then they check again. So you will know that if it's above that amount of microbial load, then you should discard the batch or whatever. And if you reach another point, so you're checking all along the stages, so you know exactly what point at which it's good and what it's not. So you'll go through, let's say you're doing a ketchup or whatever, you look from the field, you look at the conditions in the field, and it'll move, and the person handling it, you'll move to the next stage, a bottle, if it's sterilized properly, it goes through the ingredients and stuff. So at each point, persons will be there to check to see what is the critical control point within that system. So you know exactly what is it you're looking for, to whether it's safe or not. In terms of labs, that's what I know.
Right. Okay. I understand. So it's like having limits.
Yes, you have a limit. Yes.
Right. So you know what the limits are, but concerning a particular product, you wouldn't know if the product has met the limits. That's why you're testing.
Yes.
Right. So all right. So my take on it is this. So you would be testing your product, right? So you may do test 1, test 2, test 3, etc. You do several sets of tests. And at the end of doing those tests, then you will conclude that this product is safe. That would be inductive.
Correct.
Right. So that wouldn't be deductive. That's actually inductive. But if you had already, if there's some way you had already tested and you know that the product is already safe, and then you say, I'm just doing over these tests to reconfirm, then that would be deductive. Because you would.
Well, I'm guessing along that point, at the end product, you can probably have both processes going on at the same time as the end, because you'll be inductive going through the stages, and at the end, then you test. I guess maybe like a car, you can also do in the plant, and then they'll do tests to make sure that the product is already. So you can do both processes at a different point in time.
Yeah, you can. You can, and you do have both inductive and deductive approaches kind of running alongside each other sometimes.
Yeah.
So yeah.
Yeah. Okay.
Thank you.
Sure.
So I guess I'm still a little confused over how to understand what is inductive and what is deductive. I might need some extra time on the side in really understanding. I don't think I.
Okay. All right. Probably what I could do is try to come up with a couple of other examples for you, and I could send them to you, just so you know. Couple of other practical science examples, and just we could look at them. But essentially, when you're looking for your inductive, when you're looking to see whether an argument is inductive or not, what you want to look at is this argument going from a set of specific statements to a general statement, or to a generalization, right? So that's your inductive. So you're going from a set of specific statements or a set of specific facts, and then you take those facts together, and based on all those facts, the combination of those facts, you come to a conclusion, right? And then the deductive works in the reverse. So if you're looking for the deductive, you look for something general. So it has to have a general statement to start out, and then based on that general statement, you infer. You make some specific inferences.
Yes, Samuel Dominica.
Yes, Samuel.
I think inductive and deductive, they are interlinked. And sometimes if you're not very careful, you might confuse both. Because I'm trying to think about the labs that my students normally do. One, most of the time, most of the lab, sometimes to me, is like to verify the general knowledge they have. So now, if a lab just to verify what has been taught, the general knowledge they have about a topic, should I call that deductive? Because they have the general knowledge, and is it that they have the theoretical knowledge about what they want to do already before they even carry out the experiment.
But
Is
do
that
they,
deductive?
but do they know the answer? So all right. So if like I use the example, is it that you are determining, you have an experiment, you're saying we're demonstrating the boiling point of water. If we're demonstrating the boiling point of water, we all know what the boiling point of water is, right? It's 100 degrees Celsius. We know what we're going to get at the end. You understand? So
Yes.
so that is, I mean, we're not really making any generalization here. We already know what it is. So that would be deductive.
Okay. Then that means most labs in chemistry are deductive. Because before the lab is being done, they know the outcome already.
No,
Because
I wouldn't say
according
most.
to states,
I wouldn't say
because
most. I would say some. I would say,
okay.
but in some part, if we say to investigate the reaction of X with Y, right? You don't really know how X is going to react with Y, right? And so when you get your data, although in some cases you do, if depending on who the student is, right? So when you get your data, when you gather your data, it is then that you make some generalizations. But yeah, you're right. Some of these are actually deductive, because upfront you already know what you're doing. You're just kind of verifying. But there are others that are inductive. And in truth and in fact, when we talk about inquiry, which is a big thing now, when we talk about inquiry-based experiments and we talk about problem-based learning and case-based experiments, those are all inductive, right? And when you read the literature is saying this is the way we need to move. This is the direction we need to move in. So what we need to do, we need to move from giving the students information up front so that they already know, because how interesting is that? You already know what the results are going to be. Why should I do the experiment would be, an argument that a student could make. So the argument in the literature is that we need to move away from these deductive type experiments in which students already know what the outcome is going to be, to more inductive types of use of more inquiry, use of more problem-based, use of more cases, where students truly have to come up with conclusions based on the data that they gather. In fact, I could tell you a little bit about some research that I'm doing. And one of the things that we do is we, instead of starting out with an aim, for example, students come up with a question, a testable question, right? And then they go ahead and they do it. So they really don't know what the outcome is, right? Because based on how the question is phrased, they have no idea what the outcome of the experiment is going to be. So then you have different groups of students working on different things, and they collect the data. So you could have more than 20 data points. And then we collect all that data in an Excel sheet, and we look at the data. And based on the data, looking at the data, you begin to see trends. And these trends are what really lead us to our general statements, right? And so that is an inductive approach. So we gather this data, we look at the data. Are we seeing any trends here? What is that general trend? And that is where we get our conclusion from, essentially.
Sam and Dominica.
Go ahead, Sam.
Yes. Now, is it possible that the kind of words used can determine whether an experiment can be inductive or deductive. Is it possible?
All
Like
right.
the kind of word like to verify, to determine, to find.
Yes. Yeah.
Affect.
Yes.
Okay.
And that is why well, I teach another course where we talk about different types of science activities. So we make a distinction, for example, between an investigation and say an exercise. You know, is this just to demonstrate skills, or is this actually to probe stuff, or is this just to verify, or are we actually looking at something, some new phenomena? Are we truly investigating? So so the way an experiment is designed and the words that we use, etc., we can very easily turn something that is deductive into something that is inductive, or something that is inductive into something that is deductive, right? So
Okay.
yeah, but I don't want to get into all of that, but yeah. So we can do that. You can change your deductive activity into something that is inductive, and you can change your inductive activity into something that is deductive. Right? All right. Are we all still here? Take a check. Tracy?
Yes.
Yep.
All right. Good. How are you doing? Your understanding? Are we getting somewhere?
I was gonna ask, for the same experiment then, for the teacher, it would be a fact, and then the student, they're trying to find something. So for one, it's deductive, and one, it's inductive.
It is
Like
true.
if you're doing,
Yes.
pardon.
Go ahead.
Well, if you're doing the starch test with your students, they don't know that it's going to be a positive test, but you do.
Right. Yeah. So so in many cases, the teacher already knows the outcome. So as a teacher, you know the outcome. It's the students that really are investigating, so to speak, because you have designed this in such a way that they don't know the outcome, but you know the outcome already from the beginning. Does that answer your question, or shed light on your comment? I didn't hear you, Tracy. Your mic is off.
So for the teacher, the experiment would be deductive. For the student, the experiment is inductive.
For the most part, we could say it like that. Yeah.
I think that it's more of the process that you use, because if you can look at the same experiment. For example, light, refraction. Let's do reflection. And if you give the students a mirror and they measure the angle of incidence and the angle of reflection and say that they're equal, and then generalize and say that it is always equal, then that is more of an inductive process.
Right.
But if you come from the opposite end and you tell them that, listen, always the angle of reflection is equal to the angle of incidence. And we're going to take one example of this, which is with the mirror, and we get that answer being true, that's a deductive for me. Yes. I mean, sorry, yeah, that's deductive for me.
Yes, that is correct, because essentially what you're doing is you're proving something that is general, that is already known, that's established.
Exactly.
Right. So yeah, you're correct. That's correct. All right, yes, Jason. I was going to.
I thought that Ashley's question actually helped to point out another reason why induction is important in the sense of quality control. Because even at my job, I work for an environmental consulting company, and a lot of the things that we do involve environmental quality. So like you're testing specific parameters of like water, for example, and then there are certain standards that determine whether that water is good to drink. So that would be like inductive, right? Because you inductively test each parameter, and then overall
and then you make a conclusion.
Yeah.
Right. Yeah.
And then I was also thinking about like social sciences, how a lot of the direction that they're moving in is doing evidence-based stuff, even in teaching and education. So that kind of also is induction too, right? Where they want to have some kind of evidence to support whatever conclusions that they're making about education or whatever. It's based on. Would that be true, or?
Yes, it is, because it's still a little thing about gathering facts and attempting to generalize from those facts. All right. So the social sciences, I guess you could say, in a sense, it's heavily inductive, because then remember what I was saying about having a representative sample. Since they can't sample everybody, right? They're saying, okay, if the population is 100,000, they may say, all right, if I use 20% of that, I would get enough views to be able to generalize from the population, right? So they're actually using a set, and then from the set, they are coming to a conclusion about the whole, which is what it is. All right, would you guys like a little break? I just thought.
Yes.
I thought you
might. One more question, actually. It may move after the break. But I was just thinking, so like if we're not going to use this inductive approach, or try not to, try to present a different picture to students, like are there any other examples of like how to have students write like a lab report, for example, as opposed to doing it in an inductive-based way? Are there alternative ideas or anything?
All right. Okay. So when we come back, we're going to look at falsification, which is one of the alternatives that a lot of people are promoting as another way to go. All right. So we'll do an activity when we come back, and then we look at falsification. So, all right. So when we get back, so 10 minutes. 10 minutes? All right.
Okay.
Yeah. Hello, everybody.
Hello.
Good.
Hi, hello.
All right, we're back. Okay. All right, we're back. We're going to do, well, you guys are going to do a reading now. I want you to look at, I think that the document in your folder is called Fable 2. So could you access that for me? All right, so what I need you to do, I want you to read it, Fable of a Lost Child, Keeping Warm, and you can discuss it. So you can pair up again if you want. At the end, I'm going to ask you basically what are your views on the article and what you think the article is advocating. All right. So I think it's 1 page long, it may be 2. So I'm going to give you 15 minutes at first, and then you can tell me if you need additional time. All right. So you can hi Avo. So you can get a partner to discuss it with as you go along, and then afterwards you just have a general discussion. All right. So can everybody do that? Just and then
What's the name of the article again? Sorry.
The file name I think is Fable 2. Fable.
Oh, Fable.
Yeah.
Okay.
Right. So you're going to read it, you're going to discuss it with somebody, or you can read it together. And I'm going to ask you to share at the end, well, the peers to share, to say what you think the article is advocating and what are your views on it. All right, so I'm starting 15 minutes now, and then I will check in with you to see if you need more time in a little bit.
Okay then.
All right. right. Okay, folks, how are we doing on the time? Do we need a few more minutes or are we finished? Hello?
Yes, I finished reading it.
Oh, but you haven't been able to think it through yet.
I think so. It's just the 2 pages.
Yes.
Yeah.
All right. Anybody need a minute or two? All right. Everybody is ready to go. Linton?
We can go ahead.
Mm-hmm.
Yeah, ready.
All right. Samuel?
Yes, I'm okay.
All right. Okay. Tracy?
Yeah, we're ready.
Okay, you guys are ready. Ashley, you ready?
Yes, I read it.
All right. What about you, Sandro?
Yes.
All right. Okay. All right. So we're going to make some progress then. All right. So I'm going to have 4 persons sharing. Did you discuss it with somebody? Were you able to discuss it among yourselves?
No.
No.
All
A
right.
little bit.
Okay. All right. All right. All right. Let's have the more quiet people starting us off. All right. So, Linton, you want to go ahead? Start us.
Okay. All right. First of all, what I read is about well, the little boy who actually like he carried out his experiment on his own because he was in a situation where he just had to do help himself. He had to help himself, and since he was cold, he wanted to be warm, so there were bits of things around the beach. So in the first instance, he just collected things like a scientist would normally do. Pick up all, gather all the information, everything that they will need, all the materials that they would need. So the little boy did just that. And I guess lighting up the fire is like an experiment or an activity that he carried out. And from that, he was able to find the materials that would burn and also those materials that would not burn.
Okay.
So from this, yeah, he was able to analyze it even more because he needed to continue the fire. So according to him, he went back and he got other materials to carry out his experiment again, where he came back and then he assumed that everything that was cylindrical would burn, and the other ships would not burn.
Okay.
Which I guess it was, well, for him when he went the next time, it's like everything that he got was cylindrical. Fortunately for him, it worked as a sign. Just the activity worked again.
Okay.
But later on, he noticed that it was not correct.
Okay.
That basically it was like wood materials and different materials that would work. So in that, I guess, well, then there was deduction first, and then after, I guess it was induction.
All right. You would you like to all right, show us the instance where you had deduction and then where you had induction.
Okay. In the first instance, okay, I wrote something down. Okay, in the induction side, that is where he had all his materials. He gathered all his materials first.
Right.
With the deduction, is like after, like, he had the generalization, then he was able to carry out his own activity.
Hold on, Linton. So just the gathering of the material, that's you're finished with the induction, or you want to add a little bit more to that?
Okay. Yes. Okay. Well, after he gathered his information, is that he carried out his activity,
right?
And then he got results from it.
Right.
Yeah. And then with the other one, is like he had all his materials, he had his results, and from the results he noticed that it was not fully correct, and then he was able to justify it after.
All right. I'm going to take somebody else, but let me just ask you, what do you think is the author's intent?
Okay, the author's intent was to show that most people from the time they would see certain things, they would generalize it right away.
All right. Okay, hold it then. Yeah. All right. I'll pause with you for now, and then take somebody else, and then we're going to a discussion. All right. So.
Okay.
Thank you. All right. Okay. Next person. No, it's free. Ashley, would you like to share? No? Ashley? Is she there? Let me see.
I'm here. What's the question?
I was asking if you wanted to share.
Can you be more specific what you want me to share?
Oh, sorry. I had said that initially, so I thought you all right. So on the reading, I had asked you to share what is the article advocating and what are your views?
What is the writer suggesting?
Right, or advocating, yeah, that works.
He's basically just suggesting that through the process of elimination, we come to a better understanding of what facts are. Yeah, that's all I have to say right now, actually.
All right. Okay, Ashley, we'll probably come back to you. All right, Vanessa or Tracy, would you like to say something?
I'm actually working with Jason today, and he's going to be speaking on our behalf. We've been chatting back and forth.
Okay, no problem. All right, Jason, you want to go ahead?
Well, I guess your question about the author's main point, to me, I think he's highlighting, I guess it was the last point in the slide that we recently looked at, that induction is still important, especially because of so much of our scientific knowledge has been arrived at through induction. Because like in the last paragraph, he says this child is a scientist and his faltering steps will lead him to the newspapers. They are the same steps that led us to our present understanding of relativity, our discovery of polio, vaccine, and all this. So he's saying like through induction, these discoveries have been made, basically.
Right. Okay. All right. All right. So all right. Let me take one more person. Let me take somebody else before you go ahead. All right. So Jason, please mute your mic, please.
Oh, sorry.
That's all right. All right. Okay. So would somebody else like to share?
Yes. Samuel Dominica.
Hi, Samuel. Go ahead.
Yes. And also thinking about the list, the table, it noticed that all the woods, all the objects in the table 1, they are wooden objects. So from there, it make a conclusion that wooden objects normally burns. So from that, he noticed about 2 days ago that he saw a door. So he went back to go and pick the door. So it's more like a deductive approach from the generalization that table ones are all wooden materials. He left the radiator, he left the chains, he went back to the door. So it's more specific of what materials he need that he can use to make the fire.
Okay, so all right, so let's start discussing now. So Samuel, you said at what point, all right, let me ask you first. Do you see induction in the article? Do you agree? Would you say that the author is advocating that induction or the inductive approach is a useful one? Would you agree with that? Does everybody agree with that? That is essentially what you get your understanding of what the author is saying.
Yes, Ashley.
Yes.
All right.
I see both there, so I think he's trying to say both are important.
All right. All right. Can you Tracy? You point to well. All right. Can you show us a point where you think he might be saying that the deductive approach is important? I'm not saying that it's not present, but where the author is saying that approach is useful. Can you point to anything in the article that gives you that impression?
Well, after this, on the second day when his theory from the first day didn't work, in other words, like the stuff didn't burn,
right?
He took his generalization that it was the cylindrical, it wasn't just, the theory of the cylindrical burning wasn't right, so he had to, I've forgotten how, but he deduces from that, I can't, it's a deduction when because he's gone from generalization to more specifics. Because then he figures out that, I think it was the pipe didn't burn, the ginger ale bottle didn't burn, but even though they were cylindrical, something else did burn. I'm trying to find it now. Oh, the old cane did burn, and the baseball bats did burn. I don't know, so it just seems like it was more specific, not just cylindrical, but he switched. I don't know. Could be.
All right. Okay. All right. I lost my question. All right. I'll get it back. All right. So, but all right. Yeah. Yes. Somebody's.
Yes, Linton.
Yes, Linton.
Yeah. From earlier, we said that it's like deduction for like Samuel. I think he said that with at school, like the teacher, most experiment would be deductive for the teacher and inductive for students. And in the deduction part of the story, the article.
Sorry, Linton. Only some are inductive for the students. So some are verifications.
Sorry, say that again.
I'm saying only some are deductive for the student. What did I say?
Yes.
No. Right. Just kind of got mixed up. All right.
Yeah. So what I was saying, since you asked which part was deductive, I was saying the part where the child, like he generalized everything. For example, like he said that cylindrical objects burn. That he said that. I believe that is deductive.
You mean coming to that? That would be a generalized. The statement that cylindrical objects burn would be a generalization, right?
Right.
Okay, so you mean whatever he did after that, take that generalization and then apply it or use it to come up with another conclusion. That would be deductive if he starts the generalization. Yeah. Right, but in terms of getting to the generalization, that would be inductive.
Very right.
Okay, all right, I got you. All right, hold on. Let me take a question from Ashley. Yes, Ashley.
Oh, I was just going to add that the article says or says something about him going over what he had already thought was a fact. So that kind of supports the what we were talking about before, about how science is always evolving, always growing, ever expanding. So it's good to go back and check our facts and make sure that they are true.
Yeah. And
at the end of the article, it says that. Sorry?
Go ahead. I'm listening to you.
Yeah, I was just saying that at the end of the article, it states how he went back to go and check things over.
Right. So that also
check over his list.
Are you
cause the kid to go back and get the door passed up 2 days earlier?
Yeah.
So he's going back to reassess his theory.
Right. Okay. Are you finished, Ashley?
Yeah.
Okay. Because I also wanted to add to what you said, that it also helps us to understand more about the tentative nature of science that we were talking about. Because one of the things that should be clear is that sometimes induction will lead us to incorrect conclusions, or induction can lead to incorrect conclusions. You see that. And perhaps one of the things, you remember one of the things that we talked about in terms of what makes for a good inductive argument is that the number of trials that you have to do has to be large, or the number of samples needs to be large. Was one of the criteria that was put forward as something that you have to make a good inductive argument. And we had come forward and said one of the arguments against that, or one of the questions that raises is, what do you mean by large, right? So you see, in this case, where this little boy, he tested about, he tried to burn about 4 or 5, a number of things, and then based on his listing, I think it was 8 things initially, and based on what he found, he came to a generalization, and the question could be asked, was this sample sufficient for him to generalize from? Are you guys following me?
Yes.
Okay.
Yeah. I'm not sure what I didn't understand exactly what you were trying to say.
I'm sorry, Jason. What did you say?
Were you answering a question, or I didn't quite catch it?
No, I was just pausing because I wanted to make sure that you were understanding where I was saying. So I was saying, the question could be asked, was this a sufficient number of samples from which he could generalize? Because his initial conclusion was in fact incorrect, right?
Okay.
Right, and then we see where he had to go again, and then when he got new information, that new information could then be incorporated into what he already knew. So he ended up actually changing his theory, so to speak, right, for a new theory. And the point I was making also is how in looking at how he proceeded from one point to the next, we see how this might be a good illustration of the tentative nature of scientific knowledge, right? And how scientific knowledge changes over time as we get better and better information. Because you do understand that even to the end, since he has not yet incorporated the newspaper, so he doesn't have in his schema, right? He has not yet found a way to incorporate the newspaper, but at some point in time, I suppose if he's there long enough and he has need for for he's going to have need for warmth, then at some point in time it is possible that he's going to find out that the newspaper does burn too, and therefore come up with a better theory, a better understanding of what burns and what does not burn. All right. Yes.
A question.
Yes.
Ava, I said no a while ago. Is the sample sufficient? And I guess most persons would said no. Did you say no?
Oh, I didn't respond to it. I was just throwing it out there to say if it is sufficient or if it's not.
What do you think?
Well, based on what happened afterwards in the scenario, it clearly wasn't enough. Clearly wasn't enough. But no, you see, we're answering because we know there are some things that we know, which is one of the things that affects how you look at things, because the child having not had as many experiences as we have had, right? He was more limited, and that is part of the criticism of the whole process of induction, right? And yes, go ahead.
Oh no, I was just thinking. I don't think we can actually say yes or no in that situation, because we'll probably have to look at it at his environment where he was at the time and what's available. So that depending on the area he's in, let's say it's a forest or whatever. I'm sorry, so I might forget. We might say he just has trees and whatever sample he have, it might just have that available, and he might just pick up that what he sees. But maybe in another environment, he might have a larger number of things to choose from. Yeah. For example, again, if we're in the sea, we might be limited to just aquatic animals and plants. Now, if he have access to land and sea, then the variables will be different based on the environment. So I guess what he had at the moment, we really cannot say yes or no. And maybe the forest is deforestation or something happened, and that's what he had. All these factors. So that's a question that really cannot be answered in terms of was the sample sufficient. But because if we study humans and something, for example, again, if we study Africans, it might be a broad generalization, and if you go down to the different tribes and this and that, then the factors and all these variables will change. So we really I'm not sure if you understand, but that's what I'm saying. Based on what's available at that time in the environment, then a sample might be different.
Yeah, I think I understand what you're saying. But I think the thing to note is that you always, if we're going to be using a process of induction, we should try, I mean, if it is possible, to get as many facts as possible. So you gather as many facts as you can before you come to a conclusion. Because when we draw conclusions before we have, we tend to say all the facts, but you never have all the facts as we're seeing, right? But when we tend to make conclusions very hastily, many times they end up turning out to be wrong, as happened with this little boy. But would you blame him for having used induction in this case, or do you think that he was very smart in how he went about just trying to help himself in the situation that he was in?
He was very smart, and I think but in scientists. Yeah, very smart.
All right. Anybody else?
Samuel Dominica.
Go ahead, Samuel.
Yes. I'm thinking of what Eva just said. To me, I think he has enough evidence with the second conclusion he made, that all wooden object burns. Because I'm also asking myself a question that how many experiments, how many objects do you have to have before you make a conclusion? Because to me, with all what he has on that list, all the objects that burns are wooden objects. So for him to make conclusion that in the next one that all wooden object burns, to me, he has enough evidence to make that conclusion. And to me, that was why he went back to go and look for wooden door, which is not even cylindrical. But because of the experiment he did, he got enough information when he thought about it that apart from cylindrical object, any wooden object will burn. That was why he went back for the door. So to me, I'll say yes, he has enough facts to make that conclusion.
Okay, thanks, Samuel. But he also, you realize that he abolished his earlier theory that only cylindrical objects burn, because he had to abandon that in light of the metallic stuff that didn't burn. So he actually abandoned that theory. So you notice the second theory about all wooden objects burning, you would consider that to be a much stronger theory than the first, right? And yes. And so as we progress, right, you notice that the theories are getting better and better and more resistant, then, if we can use that term, right, more hardy, and so you see a natural progression. The only issue now, I think, is that he might be thinking that only wooden objects burn. So he has not yet got to the place where he can see that there are other types of material outside of the wooden ones that he can also incorporate into his scheme of things. All right, but did that give you a clearer understanding of induction?
Yes, I think so. It's very simple and easy to read, and I mean, you could follow it.
Okay, very good. Did it help, Tracy?
I'm still trying to wrap my head around it, but I think the examples are the way I learn things, so it was helpful.
Okay, all right, good. Because the thing is, most of the articles, if you read all the articles that I've pointed you to, they tend to be reinforcing each other, because the points are made again and again and again, right? Similar points. So I want just take your time and see if you can go through the different readings. And as you do that, you will see that, you know, the same points are being reinforced, are being made, but because it's being made by a different writer in a different style, you know, it aids your understanding. And so by the time you've read through them, I think you should have a pretty decent understanding of the induction and the difference between induction and deduction. I'm hoping so. All right. Okay.
I guess I kind of have a question related to that, but go ahead. Well, something I was thinking, doesn't it also involve falsification to an extent? Because once he's got new evidence, then he's rejecting.
Exactly. Yes, it does. It does, in fact. But because we haven't talked about it as yet, I didn't want to bring it in. But it does. It does incorporate some degree of falsification as well. Yeah.
Okay.
All right. So we're going to start talking about falsification now. So let's get there. All right, so finally, we've been hinting at it for a little while. All right, so one of the main proponents of this falsification approach to scientific knowledge is Karl Popper, who was born in Vienna. And essentially, Popper has been like one of the greatest critics of induction. He writes scathingly about it, and he describes induction as a myth, right? You may recall that Driver, who we just looked at, called it a fallacy. Well, Popper says it's not just a fallacy, it's a myth, a complete myth. So he has been a really, really strong critic of the inductive approach. And he puts forward his alternative, which he calls the hypothetical deductive approach, which is the same as the falsification. All right, so we want to take a little bit of time to see what this approach is and what he says. All right, so of course he has, in just putting forward his approach, he has put forward why induction doesn't make any sense. He just reiterates, and he says induction does not lead to logical and true generalizations, or even to ones which are probably true. And the reason he says that, of course, is because of the limitations that we have cited, and one of those would be that Popper is strictly saying that you cannot generalize if you don't have the whole, if you haven't a full sample. So he's saying the fact that you may have not taken everybody in, or all, you don't have all the facts, then you can't have true generalizations. So his point is, in order to make true generalizations, you have to have all, absolutely all the facts. All right. So that's one of the things that he says. And then he says that a point that we have made time and time again, he says that observations actually assume theory. So when we make observations, we do them in light of our experiences, our prior knowledge, etc., etc. All right. And then he says that theories can only be speculative and tentative, right? And they have to be subjected to rigorous testing and experiment. And when those theories are subject to testing and experiment, he thinks that any theories that fail under even one observation, those should be eliminated and be replaced by speculative conjectures, which he's referring to are really hypotheses in a sense. All right. So he has a whole list of stuff that he's really trying to hammer home. All right. So let's look at what at this falsification then. All right. So these are the main claims. All right. So the first thing, he says, rather than science beginning with observations, he says science usually starts with problems, right? So you think about, you have a situation or you have a problem, you come upon something that you need a solution for, right? And that's how you begin to operate in the scientific realm. So he says science really starts with problems, and then having a problem, the hypotheses are proposed as the solutions. And he uses, well, when we talk about falsifiable hypotheses, those are hypotheses, they can be proven to be false, all right? Now, in talking about hypothesis, Popper makes a point that your hypothesis, to be a good hypothesis, it should be as wide-ranging as possible. That is, it should be what he calls highly falsifiable. That means it would be easy to prove whether it is true or not true. All right, but we have some criticisms of those that we will come upon in a little while. So we'll come to that later. All right, and then the hypotheses are to be tested. And some hypotheses will be eliminated, while others will be subjected to more stringent testing and criticism. So I'm not sure you can see this very well. If you can't, it is in your folder. It's in the folder that I sent you. It's I think it says Popper something, right? So if you can't make this out very well, then just look at it there. All right. But essentially, this is how Popper thinks that scientific knowledge actually progresses or is arrived at. So if you look where you have an idea, notice all those points that are kind of flowing into the idea. So provocation of unsolved problem, your experience, existing hypothesis, insight, and tuition. So all those are things that Popper is saying, all of those influence this idea, right? Ideas that you have, or that, yeah, this idea. And then from your idea, you come up with a hypothesis. Now, you have a hypothesis, and the plan is to test this hypothesis as rigorously as you can. So your hypothesis is subjected to rigorous testing. And when you do that, there are two things that could happen. Well, it could fail under the testing, or it could, well, I don't want to use the term pass, but it could not fail, right? If the hypothesis does not fail, then notice that it leads to scientific knowledge. It contributes to scientific knowledge. But if the hypothesis under testing has failed, then we kind of have a loop, and it loops back to you come up now with a new hypothesis. And then the process starts all over again, all right? So essentially, this is the process of falsification as described by Popper. So I have a little question. Does it remind you of anything, or does it look like anything that you know? Or sound like? It probably not look like, but sound like. Anything that you're familiar with?
Yeah, Samuel and Dominica.
Yes, Samuel.
Yes, what comes to mind is more like the planning and designing that we normally give to students.
Right.
Because in every planning and designing, they will have an idea of what they want to do, and from the idea, they will write an hypothesis, which is more like a guess. So, and from what I'm reading from what you just said there, the hypothesis can become true or false. If it becomes true, then it becomes scientific knowledge. And if it's false, that means they have to start all over again. So to me, it's looking more like a planning and designing experiment. How student or teacher goes about planning and designing an experiment.
Okay, good. Yes. So it does resemble somebody else? Somebody else?
Like the scientific
Yes,
method.
yes, Ava.
It looks like the nature of explaining the nature of science, the scientific method.
Okay, the science. No, remember the scientific. Remember now. What do you mean when you say the scientific method?
We're going through the nature of science. What you have to do, have an idea, run your hypothesis. You go, you test it, and then you go yes, no, accept it, no, in a kind of a way, small scale line.
Okay, because the reason I ask you that is because we have to be careful, because when we talk about the scientific method, remember, we normally use that to refer to the inductive approach. So you have your aim, and then you do your method, then you do your, you have to take your results, and then, right? We use it. So when we refer to the scientific method is normally used to refer to induction. So we have to be careful how we use it. All right. But yeah, so I was saying, yes, it is pretty much, and this is where our planning and designing, our approach to planning and designing has been taken from. It comes from this falsification approach, this hypothetical deductive approach to scientific knowledge. That's where it actually comes from. And one of the things that teachers, I think, tend to try to press home to students is to make sure that they have very good hypotheses to begin with. So one of the criteria for a hypothesis, when you were marking for hypothesis, certainly on the CSEC, is that the hypothesis has to be testable, right? It has to be a testable hypothesis. So you can't start out with something that is not testable, that is not appropriate. You have to have a good hypothesis to start out with, and this is key to Popper's falsification process, right? Because the hypothesis must be stated in a form that can be falsifiable.
I have a question.
Yeah.
It's for Ramita. What is the design and planning that you're referring to?
Oh, sorry. Okay. All right. So, in the CXC syllabus for the sciences, part of what students are required to do is, well, there are several skills that students are assessed on as part of their SBA, their school-based assessment. And one of these skills is what we call planning and designing. And planning and designing, essentially, what happens is that the teacher may come up with a problem. So for example, let us say that the problem is that Mr. Brown realizes that his roof, his house, his beach house, yes, let's call it that. So Mr. Brown has realized that the roof on his beach house rusts to a far greater extent than the roof on his house, which is much farther inland, right? So let us say that that is the problem that the teacher poses and puts forward. And so the teacher poses a problem like that and may give the students instruction to now plan and design an experiment to help Mr. Brown to determine whether or what is the cause or some such thing, right? So the student will then think about it and say, okay, so Mr. Brown's roof, the one near the beach, that one is rusting. The one further inland is not rusting as much. So the student thinks and says, okay, so in my experience, in my exposure to science, which aspect of science does this relate to, right? So the student will first have to do that and perhaps come to the point where they realize, okay, perhaps it could be the salt, the effect of the salt, right? The effect of the salt solution that is causing the increased rusting. And so based on that, now the student comes up with a hypothesis and says that roofs that are near the sea will rust at a much greater rate than roofs that are inland due to a higher salt content, etc., etc. Do you follow what the point I'm making?
Yes.
Okay, good. So the student starts out with a hypothesis, and then the student will now have to plan an experiment that they could do in the lab at their school, right? That would test whether their hypothesis is true or not true. The students are now required to at least carry out one of these planning and designing experiments. And so they would carry it out pretty much, so that would be where they would be subjecting it to testing. And then if for example, their hypothesis is not supported, then they would say that it is not supported, right? Or if it is supported, then they would say. So essentially that's it. I hope that kind of covers it, unless anybody else has anything to add that you think might clarify the process of planning and designing a little bit more for us. But is there anything else? Yes, go ahead.
I have a question. It's related to your example as opposed to the course. How old are the students when they have to do this? Like planning their own experiment and actually performing it?
4th and 5th form. That's where they start. But well, 4th and 5th form for the purposes of the exam, but in terms of introducing it to them, teachers could introduce it to them much earlier, like grade 7.
Grade 7, yeah, they start with that.
Ava, that was muffled. Just say that again.
I said from one, you just have basic knowledge of it. Once you introduce it to them, yeah.
Okay, right. So you
What
can.
age is that, sorry? What age is Form 1?
12, the oldest on 12, yeah.
Okay.
Yeah, but you, in truth and in fact, you could expose them to this way of thinking, like in the primary school as well. They could be exposed. You wouldn't require them to probably. You would use something which is much simpler, a much simpler example. But they could be exposed to this because it's a particular way of thinking about a problem. It develops problem solving skills, right, and help them to kind of think outside of the box, because now they have to think of options and possibilities for those things. What could be causing this, etc. But in case you are concerned that they may not have sufficient ability to do this, they often kind of share their ideas with their teachers, right, and get feedback on whether their proposals are making any sense or not, or how they need to change. So it's a pretty fluid process where they are in discussion with their teachers about the hypotheses and the plans that they have come up with to design their experiments. So yeah. So I'm going to suggest for those persons who are not familiar with the planning and designing or the CSEC syllabus in general, if you get a hold of a CHC syllabus, there is a part in it that talks about school-based assessment, because I think at least you need to read about planning and designing. So there is a part in it that talks about school-based assessment, and you can read that. You can use any science syllabus, because it's pretty much consistent across the board for that, to take a look at it. In fact, the next assignment that you're going to do will have something to do with that. So it's going to kind of push you to do that reading that is going to become necessary.
Yes, and we have an assignment based on the CSEC report due very soon. So.
Oh, okay.
And others.
Okay.
We have started a different report over a 4-year period and comment on it, do an assignment on it. So we will have access.
Oh, okay. All right. Yeah. Okay. Good. All right.
Is it possible for us in Bermuda to do it on another exam like IGCSE, or even if we could do it on our local public, whatever kind of assessment students do here?
You mean for my assignment?
Yes.
I would say no, and I'm not saying no because I wouldn't want to accommodate you, but because what is the extent to which you would have to look at the syllabus is a very limited extent. All right, but all right, tell me though, do you do something similar?
Well, I guess IGCSEs, but in the public school system, it's different. In private schools, they probably do IGCSEs or, yeah, basically, I guess would be that.
Yeah, but I mean, in terms of the planning and designing, do you have something that is similar to this particular?
I don't know. I wouldn't be able to answer that.
Oh, okay. I thought you knew what that was. All right. Yes, Tracy? Oh, no.
The IGCSE is very similar to the CSEC. And for Jason's benefit, the public schools are going to that in September, either this September or next. So it is something to learn about. But they're very similar. Like the reports and how the exams are fairly similar. I've had a look at the CSEC last week or so.
Okay. Thanks, Tracy. All right. So any other comment before we move off Papa's little flow chart here and continue?
I do have a question about pathway A. it refers to one of the myths of science that we talked about. It says, unchallenged by experimental evidence, the hypothesis undergoes evolution to the status of a theory. So I'm wondering if that's actually true, because that's not, that's like I thought that was one of the myths of science that we looked at before.
Which part exactly?
In pathway A, it says that the hypothesis evolves into a theory.
Oh, okay, I understand what you're saying. Okay. Well, yes, in a sense, but what it is saying really is that it's not really the hypothesis itself that evolves into the theory. Because remember that based on the hypothesis, you would have carried out the experiment, and from your experiments, you would have gathered your data. So it is the data, actually, that that forms the theory, right? So right. So it's actually the data that would be the basis of that. So so the hypothesis would have undergone rigorous testing, and having passed through those tests, right? So it would be like gathering positive data, if you want to call it that, right? So having passed through those stages, then you form a theory. But the truth is that a theory, according to Popper, right, is slightly different, because a theory for him is not something that is etched in stone or that is even true. His conception of a theory is something that is tentative, because once there is one piece of evidence that contradicts it, then that theory has to be abolished, and essentially process starts over again, right?
That's not true with induction?
Not completely, because with induction, they tend to, all right, so for example, you have a theory, right? And that theory, there is a lot of evidence that would have established, well, hopefully, a lot of evidence that would have established that theory. The first bit of, let us call it, evidence that comes along that proves it to be untrue, in induction, you may not necessarily right away say, all right, this theory does not any longer hold, right? With induction, what may happen is that you would have to now gather a certain amount of evidence in order to abolish the theory. With the falsification, it says once you find a single piece of evidence would falsify it.
Okay.
Yeah. So it's a little bit different. All right, let's proceed. All right, so so pretty much this is some of what we've said. So according to falsification, scientific theories cannot be verified. You can falsify them, but you cannot verify them, right? So we can't ever say in falsification that a theory is true. We don't say that, because falsificationists don't really talk about truth. But what we can say that at this time, this is the best theory that we have, right? So you see where the difference comes in now. So the falsificationist always leaves that kind of little room for doubt. So we're saying this is the best theory, or this is the best explanation we have at this time, right? But we can't say that this is absolutely true. All right, and then I have the point here about the theory. The theory needs to be able to be highly falsifiable, which I made earlier. All right. So some of the arguments that have been put forward against falsification. All right. So as you know, I mean, there are arguments for and there are arguments against. All right, so first argument is that not all experimentation is based on conjectures or hypotheses and refutations, and that is true because every experiment does not necessarily start in the same way. So that's one argument, and a big argument is that really this theory of falsification or this idea of falsification really is kind of misguided, because it's saying that essentially as a scientist you would have to be setting out, you want to put forward a highly falsifiable theory, that is that your theory can be proven wrong. And the question is, does anybody actually set out to have your theory falsified? I mean, if you come up with a theory, would you want to make it easy for somebody to disprove it? You know, so the point is that falsification probably presents a strange view, a view that is not consistent with true practice of science, right? Because you don't want your theory. I mean, if you come up with Ava's theory of aerodynamics, you know, Ava would like that theory to last for years and years and years, and for students in schools to learn about it. So she's not going to be setting out to prove her theory wrong, right? Scientists just don't really operate that way. So yeah. And then as I said, there is no truth in falsification, right? You never can attain truth. We can only say, hey, this is better than everything that has come before it. But we can't say it is true, but we know it's better. All right. And the point also is made, which kind of relates to the question you asked before, Jason, about if in induction, as soon as you have new evidence, if it does not, if you don't just change the theory, right? So this latter point here says that if falsificationism had been applied, right, on all the theories that we have in history, we would never have had any scientific results, because as soon as you found one piece of evidence or one fact to contradict something, you would have just canceled that totally. All right. So these are some of the main arguments against falsification. We can take a break here. Are you up for a break?
Yes.
Okay, I was wondering if you were already on break. Okay. All right, so let's take 15 minutes.
Okay.
All right. Hello, everybody. Are we back?
Yes, I'm here.
All right, Tracy.
Yes, I'm here.
All right.
Yeah.
I'm here.
Okay.
Yep.
All right. All right. You're going to do a little activity now. Work activity. All right. So for this, I'm trying to remember the name of this now in your folder. All right. I don't remember. Just let me check for the name of the file so I can tell you. Okay. Yeah. So the name of the file that you need now is Classroom Experiences.
Where is that located?
Who is it? Ashley?
Yes.
Ashley, you didn't get my email. I sent you the files separately from everybody else because you said your computer couldn't download the folders.
The last email that I got from you was the facts, laws, and theories PDF.
Right, that was this morning. No, I sent these from last night. I sent the stuff for the class the day before.
No, I didn't get your email last night.
So hold on. Did you get the fables thing we were reading earlier?
Yeah, Jason sent that to me last class.
But I sent all those stuff to your email, to the same email that I sent to this morning. That's very strange. All right. All right, Jason, could you send her the classroom experiences, please, or somebody just send the classroom experiences to Ashley?
Thank you.
Sure, no problem.
Someone sent it already?
Mm?
Did someone send that to Ashley already?
I don't think so. Just go ahead and
Oh, okay.
All right, and then so what I want us to do, I want everybody, we're going to work on 2 cases, one at a time, because I want to kind of spend a little bit of time on this. So we're going to take case 1, and I'm going to ask you to go through case 1, discuss it with somebody now. So make sure you partner up this time, everybody. And then I want you to attempt to answer the questions that follow, and just to bring to bear all that we have said so far. You try to incorporate all that you know about what we have said to your response. All right? So we're going to take case 1. We'll discuss it and we'll all work on it. And then afterwards, we'll take case 2 or case 3. All right? We'll work on at least 2 of them. But depending on how much time we have, if we have sufficient time, we'll just work on all 3 of them. All right? And then after that, I have one little, let's not call it little, I have one more activity, and then we'll wrap up after that. All right, so case 1, I think it's not very long. It's not, I don't think it's too long. So I can give you, you probably need like 5 minutes to read it and probably another 5 to 7 minutes to discuss it. So let's start off with 10 minutes and then we'll see if we actually, you need all that 10 minutes or if, if you need more, all right? So I'm just checking with you. So 10 minutes on case 1, please. And remember now, have a partner to do the discussion and then we'll talk about it. Is that clear? All clear?
Yes, yes.
Okay, good.
I think so.
All right, okay.
Hello, Ava? Ava to Ashley. Ava to Ashley.
Hi, Ashley.
Do we need a few more minutes?
Yes, still discussing.
Okay, all right. Are we ready now?
Kind of.
Kind of. All right, kind of sounds good to me. You ready now, Sandro?
Okay, you can go ahead.
All right. Linton and Samuel, are you guys ready?
Yes.
Yes, you go ahead.
All right. Okay. So, which pair would like to go ahead first? Let's have a volunteer. And you can the first, you can just start with the first question, and then we kind of carry on like that.
Okay, I and Sandra, we can go first.
All right.
Yes, in our discussion, we noticed that the expectations of the students was totally based on the observation was totally based on the expectation, and that really influenced all the outcome of what they observed because of their expectation. And also, we also noticed that the age is also a factor, that the outcome, the lack knowledge of, should we say, what they did, and they will need some assistance from teachers, from a teacher to help them. And I think the teacher can come in helping them with experiments to really verify and to prove what they're trying to do and how they can easily know. For example, if you talk about the air in the jar, I was discussing with Sandra that they can use sound experiments, because even if they remove the lid from the top of the jar, will not affect all the air in the jar to go out. And to do that, you can just use a sound to test for sound in the jar, because once they see some air in the jar, you will hear a sound or like of a bell. And the only way the only way you can remove all the air in a jar, you have to use a vacuum. So maybe
Right.
teacher can help them to know that no matter how you open or you the jar, the air will still stay there, and the only way is just to test the sound because of vacuum and all that. Sandra?
Thanks, Samuel.
Yeah, that was pretty much what we said. I think I just want to add to it that in terms of the age, we were saying that at 8 years old, they probably hadn't yet developed the level of logical reasoning that is required to make the links that the teacher wanted them to make. And so that would have been a hindrance in the learning process.
Okay. All right. Thanks, Sandro. I'll take somebody else. Take another pair. Everybody's gone quiet on me. Who'd like to go next? I don't want to call any names.
Okay, I'll go. But I didn't really like this exercise because I didn't really understand it, and it doesn't seem like the kids understood it. I guess they're just repeating things that they had heard, like someone told them, don't take the lid off that because the air will get into it, or it seems like it was things that they had heard, but they didn't really understand why they were saying what they were saying. To me, that's the way it read. So that would go with Samuel and Sandra's, where they were just too young to have logic, so they were just repeating things maybe that they had heard. I don't know. That was my take on it.
But even though they may not have developed the base for logical reasoning, would it have been impossible for them to observe, to just say what they saw based on the activity that they were carrying out?
I guess for the second part, yeah, but unless you do what Samuel says and make a vacuum, I don't see how they could see air going in and out of a jar.
Okay, all right, that's true. All right. Next one before we.
Ashley from Bermuda.
Yes, Ashley.
Just to add to what Tracy was saying, they could have fixed a syringe somehow to the jar to kind of show what happens when you suck the air out.
Right.
Versus just putting the top on it. I just thought about that just now.
Oh yeah, that's true.
Syringe.
Because they would see the movement of the piston. All right.
Wouldn't that be the same as what Samuel said? Making a vacuum, you know how you have the bell jar, the bell jar with and you attach a vacuum and you suck all the air out of it. Isn't that the same thing?
No, that's not quite the same as a syringe. No, it's not quite the same. But I mean, it would achieve similar objective. Because what you want to do is to let them see that there's actually something in there. It's not empty, in inverted commas. All right, but everybody hasn't shared yet. All right, so let's go. Samuel just spoke to me, right? Jason?
Okay, sorry, which question are we on?
The case one.
Right, which part?
Okay, we could go to, would you like to talk about what it suggests about helping students? I think somebody else's mic is on. What it suggests about helping students develop their observation skills?
Okay. Basically what I said, I was discussing with Vanessa, and what I said was that it shows that the teacher needs to be aware of the kids' preconceptions and even misconceptions.
Yeah, very good.
Where they teach them, and so you take that into consideration to understand exactly what they need to teach and strategize how they can go about helping the students to overcome the misconceptions.
Mm-hmm.
And then also Vanessa mentioned, I think she basically mentioned that it also shows how like induction needs to be done. I think she said not just one time, basically. It needs to be done. Observations need to be made a lot, I guess, to help or like by different people. Like it will help to take away the biases if many people are doing it to get the same results, kind of thing.
Okay. But yeah, and I suppose even if you are doing an experiment, you need to, depending on the nature of the experiment, if you can run it more than once, that would help as well, just to make sure that the results that you're getting are, what you think you're getting. So like an experiment like this, where, well, I'm not sure what the results are because it's very shady in terms of what the students have reported. So in terms of repeating the experiment. But what I want to reiterate from what you said, which is the important thing that I think in this second question about helping students to develop their skills, would be the fact that teachers have to pay attention to the preconceptions that the students bring to the classroom environment and start from there. Because a lot of times we carry out activities without first asking the students, some questions that would help us to understand at what the point that they are at. because if we don't understand where they are, we're going to probably start at a different point, assuming that they have certain understandings when in fact they do not, right? So I think the teacher could have started with understanding where the students are at and then take them from there, right? So question them about why is it that you think that there will, if you take the jar off, that the air will come out, right? And when the jar is on, etc. So all of those things have to be taken into consideration. And as you said, there are little activities that the teacher could then do prior to this activity that would help students to understand air, right? Just the nature of it. Right. Yeah. All right.
I guess I actually kind of jumped to the third question when I was mentioning Vanessa's point, because she's unable to talk because her mic doesn't work. But she made another point that was really related to this question, which I think is relevant. It says that also to develop their observational skills, they should be encouraged to consider multiple possibilities. So they're not only considering what they think is most likely, just to be open to consider other possibilities.
Yeah. And well, the thing about it is what is interesting about these students here is that they don't seem to be, what they have come away with from the experiment is like totally different from what is happening in the experiment. In fact, they could not have done the experiment because essentially what they are reporting is their own views. So even though, for example, they were seeing the water in the jar, one girl was saying there isn't any water in the jar because the water can't get in. So even though it was obvious, it would have been obvious that there was water in the jar, but she was like, no, water can't be in the jar. I mean, she had already, pretty much started from a position, the water won't be able to get in, and ended at that same position, right? So, so there really is need for intervention there. And then even though they saw that the water went up to a certain point and wouldn't go any further, she's like, so what's in the teacher, when the teacher asks what's in the rest of it, she's like, there's nothing there. So the fact that they said that they understood that air was everywhere, they weren't applying this everywhere, did not refer to the jar. The jar was considered a part of everywhere. All right, let me take a question from Ashley.
Yes, I was just going to say that if the students were actually observing what was going on, like the teacher could have had them gather around and carefully observe, rather than just assume that they knew what was going to happen. That would have probably helped the students with their question 2, helping the students develop their observation skills. Actually, have the students come around, like I said, and look at what's going on rather than just, I don't know, what the teacher was having the students do, passively look on, or actually like look into the jar as it's filling up with water.
Yeah, and sometimes too, when we may be having an experiment, so an experiment is going on and we say to the students that they should observe and write down their results. I think that an instruction like that is too vague, we need to be more specific. So for example, if you're heating something in a flame and you just say to the students, observe, the student may pay attention to the wrong thing. So you may want them to see that something is expanding, for example, or that a gas is being given off, but the student may say, oh, the color of the flame is changing. That's not where you want them to focus their attention. So in terms of giving instructions, sometimes we have to be far more specific about exactly where we want, especially with the younger children, exactly where it is that we want them to focus their attention at this particular time. So you may say, okay, look at the color of the solid. do you see any changes there, etc. Right? So that will help them to understand what is important in a particular case.
Yes.
Okay.
Thank you.
Sure, no problem. All right, so what conclusions can we draw about induction now? Let's see if we can draw some conclusions about induction here. Because you see that this is supposed to be an inductive activity, right? Where the students are supposed to make observations, and then based on their observations, they're supposed to arrive at some sort of conclusion. But as it is right now, I don't think there's any conclusion that they have arrived at. They're pretty much nowhere. The teacher is going to have to tell them, exactly what is going on right here. All right, so what conclusions about induction can you draw from this activity here? But what did you have as, what did you write down?
Yes, Samuel?
Go ahead, Samuel.
Yes, what comes to mind is once the premise is laid down is wrong, for sure the conclusion will be untrue. So the premises laid down by the students, Jane and Sarah, was wrong. So the outcome conclusion can never be true.
Okay, all right, that's true. But Samuel, shouldn't the conclusion that the students came to have been based on their observation?
Yes, but like I said, the premise they laid down was not true. So automatically the conclusion also will be affected.
All right. Okay, so link that now to induction. What does that lead you to conclude about induction? I know that's not an easy question. Oh boy. All right, well, if not that one, do we have any? All right, who is that? Yes, Ava?
That the facts are not really considered facts because
Ava, we're getting a lot of feedback, Ava. All right.
Sorry. The facts are not really, cannot really be said to be facts per se. Maybe they have a bit of falsification inside of it. I don't know. I think.
But could we say that generally about induction, though, that the facts are not facts per se?
No, not generally, but you mean in that case?
Oh yeah, because I think what the intent is that we make some general conclusions based on what we have observed here about induction. All right, so since no, let me ask. Oh, Linton.
Yeah, I'm there.
Do you have any conclusions that you drew from the experience here that you want to share?
Well, basically, it's almost the same as what Samuel concluded.
All right, that wasn't exactly about induction, but okay. All right, does anybody else have anything before I just make 2 points or one?
I think just that it is not completely unbiased. Our observations are not completely free from our preconceptions, and it's not completely objective, the act of observing. On
point, Jason. All right, excellent. That is key, right? That is one of the things that we want to bring out from this activity. The fact that observations are not unbiased, right? They are in fact biased. They are colored by our experiences. They're colored by our preconceptions or prior knowledge, by a number of things. All right, so on point, Jason. Very good. And linked to that is the fact that induction is not a straightforward process, a process as the proponents would want us to conclude, right? Because it's obvious here that we do not just simply go from facts to theory, because look at the difficult time that the students are having, right? And yeah. All right. Yes, we can leave it here. All right. Any other thing on this? No? Are you guys? Yes?
I was going to say, I can't remember the slide, but it was one that Ava had asked a question about where it talks about facts, or the observed thing, not necessarily leading to true facts, I guess.
Yeah.
We're observing things. And they're saying, so that's a fact because they observed the phenomenon, but it's not true because it's not actually what's really happening.
Right. It's not consistent with, well, what is it? Not consistent with truth. Yeah, I remember. Yeah. Right, because yeah, the observation, you make the observations, because remember, one of the things, is that there is really a difference between your observation and your fact. Your fact is really the statement, right? But for the inductivists, there is the inductivists say there really is no difference between your observation and your fact, because I mean you are 100% unbiased and all of that, right? And it is just bringing out the point that cannot be true. It really is not true, right? There really are many, many other things that impact on what comes out at the other end. All right, I hope you guys are not too tired. I still have one or two little things for you to do. All right, so what I'm going to do then now is break up the other two cases. So can we have 4 people on case 2 and 4 people on case 3? So we'll take a shorter time. All right, so could you just indicate if you want to be on case 2 so that we don't have everybody on one case?
I think we'd like to do case 2.
All right, that's Jay. We can take 4. Jason, who are you working with again?
Vanessa.
Who?
Vanessa?
Vanessa, right. So we can take 2 more persons on the same case, and then 2 more, and then the other 4 on the case 3.
Can Ashley and Ava take case 3?
Sure. So Ashley and Ava, and then we can have another group. Samuel, which group do you want to be on? Which case do you want to be on?
Yeah, 2.
All right, and who you working with?
Sandra.
Sandra, right. So that means that Linton and who is left?
Me, Tracy.
Tracy. So Linton and Tracy, you'll be on 3 as well. All right, so you have more people to think it through. All right, so 10 minutes should do it. I'll give you 10 minutes. Ready, Linton?
I
was just checking if you guys are ready.
not ready. We're still working.
Okay, all right.
sure your microphone is on. The breeze is blowing into your microphone.
Sorry. Sorry.
Are we ready now?
Yes.
Yes.
Okay, great. So we'll take the twos. You take number 2. Who will start?
Okay, so Samuel and I were working together, and we noticed that the students were actually making correct observations, but the teacher was only looking for one.
Yes.
And so because of the teachers, trying to get them to just answer heat, he or she ignored the fact that the vibration and the sparks were also examples of energy transformations. And finally, the teacher got so fed up with trying to get, heat. The teacher gave the answer himself or herself.
Yes.
So we thought that was sort of destroying the whole process.
Yeah, because the teacher was kind of hooked into this particular answer that he or she was going for. And I mean, if the students didn't get that, then, that was good. Right.
So we thought that if you want to teach students how to observe, you should teach them to use all their senses, 1, and 2, as they were doing the experiment, to record in an unbiased fashion everything that they had seen, touched, etc.
Yeah. And yeah, all right. Some other people worked on it. Let me hear what. Yeah.
Okay, yes, to add to what Sandra said, I think when it comes to transformation of energy, the teacher should know that there are different and many forms of energy. And also the sparks, which is also a light energy, should have been included.
Right.
But to add to what Sandra said, the teacher only focused on heat energy, but light energy is also a form of energy. So as
it's vibration.
Exactly. The teacher has limited or narrow minded about transformation of energy itself.
Right.
And also what I notice is when it comes to scientific observation, once what is observed as a fact, the teacher should have accepted what the student observed and discuss more about it.
Right. Yeah. I agree. I agree with you guys. I think I don't have a problem with the teacher expecting heat, right? But in terms of, okay, so they did not observe heat because Paul said sparks. I don't know, because he was saying sparks. He saw sparks, but he don't know about the heat, right? Which the teacher kept talking about. So of course, all of that could be explained. That I mean, there are various forms and you could lose energy in different forms. I mean, not lose is in quotations, right? And help the students to identify, okay, so probably you didn't feel the heat energy, but there was this and there was this. And another thing was kind of related to what we had said in the previous case, where we were talking about the fact that if the teacher wanted the students to observe heat, then perhaps she or he should have asked them to feel, when they were doing the experiment, make it a point to ask them to feel wherever it is that she wanted it. She thought that the heat was going to be transmitted. So she would say to them, okay, so after you do that, feel it. Do you feel any change, right? Is there anything that you feel, you know, etc.? Because to sort of guide them into what it was that she wanted them to observe, as well as the other things that they observed, so that they could get a fuller picture. Because I think probably the heat was the dominant form, and she didn't want to miss that. But I mean, there are other forms as well, as you guys said. But yeah, but more guidance into what it was that she wanted as well, or he wanted. All right. So does this as this case is laid out, do you think it supports induction or not?
I guess we can go because we haven't spoke about it yet.
All right.
I guess for me, I didn't think that it necessarily supports or denigrates the induction. It just kind of shows the limits of it, which is important to be aware of. So it could not support it if you want to use it in a certain way. It might not be the best way because of the limits of it. But we also thought that it shows that you could be you have to be looking at the correct thing, or like you can, there's a tendency that you're going to find what you want to find, what you're looking for, which can cause you to miss out on other important pieces of information. So like if you're trying to solve a problem, you have to be looking at the right thing. That's the solution to the problem. You can't be but because of your expectations and your selection, you might be focusing on something else, I guess.
Yeah, that's true. That's true. I suppose if the experiment had worked the way it was supposed to work, then because I think the teacher was using these various things. So and his or her aim was that the students would see that heat was transmitted. So if case, I think somebody's mic might be on. It's yours, Jason. Your mic.
Oh yeah, sorry.
Right. So if in case one, where they used the electric bell, if they saw that heat was given off in that case, and the battery, then the dynamo and the light bulb, and etc. So these various instances, if they were able to say that and then bring all those facts that they derived from their observations and then make some sort of general statement, then it would have supported induction. But the fact that it didn't work so well, I suppose, it points to some of the issues that can arise when you use an inductive approach. But I think it is a little bit more than just the inductive approach. It also has to do with the fact that the teacher did not provide the students with sufficient support.
Clear instruction, yeah.
Right. And so that is another important thing that we want to look at when we ask students to carry out experiments. How much support do we give them? You know, and you know, are we there to see that they are actually on the right track, etc., etc. All right. I was
thinking we had another point, but I was just thinking maybe it's more deduction, because we're suggesting, or Vanessa suggested, that the teacher could have like given them like a thermometer, a specific instrument or something that could, and tell them, okay, you can measure temperature.
Okay.
That would be more deductive, wouldn't it, though? Because that would be going from saying, okay, generally that heat is emitted.
Well, not really, because I mean,
no.
I suppose in giving them the thermometer, you're not necessarily saying that heat is going to be given off, or some instrument that they could use, but you could be saying, I want you to find out if there is any change in temperature. Because it could be that they're, you know, sometimes you have these, you give them an instrument, they don't necessarily, and everybody's like, but miss, It's not changing, right? But that is what is supposed to happen. You know that that is what is supposed to happen, right? So it wouldn't necessarily be deduction, right? So yeah, that's
Also, Vanessa had this YouTube link to a short video which kind of relates to this. Yeah. I don't know if we had time to look at it, but I think it would be kind of interesting to see what everybody would think about it.
All right, so you can share.
Okay. Vanessa shared it and I shared it. I think it both will work, but maybe it's best to use Vanessa's one if you found it first.
Okay. Which one is it? The first one or the second one?
The second one.
Okay. All right.
From Vanessa.
All right. Yeah.
How many passes did you have? Right answer, 15. But did you see the gorilla?
I did.
This video is from Search by Daniel Simon, commercial free, and is copyrighted.
Yeah, thanks, Jason. That's really, that's actually very interesting.
Yeah, Vanessa was the one who brought it. Has everybody watched it yet?
I watched it. Did we all watch it just now?
Yeah, I was wondering if everybody else watched it.
That's what I'm asking.
Oh, okay, sorry.
No.
Oh, you didn't. All right.
Yes, I saw it this week.
The question though about if you saw the gorilla actually.
Right. Vanessa was saying that they did it, and like 80% of the people who watched the video didn't see the gorilla the first time, and some of them even argued. Some people argued that there was absolutely no gorilla, like they just denied it.
Yeah, and yes, and that is true. Similarly, in science, I guess the point we're bringing out is that sometimes when you actually, your attention is focused on one particular thing, then you miss everything else. And sometimes, and so it goes back to the point that sometimes the teacher actually has to kind of push the student in a particular direction if there are really, really important things that they want them to see, not to miss. There's going to be a need for that. All right, thanks guys. All right, we're winding down, so let's take those persons on 3, case 3.
Yes, Ashley from Bermuda.
Yes, Ashley.
Basically, there were various hypotheses.
Can you share
that the students? Daniel, there's 1, 2, 3, 4 people who are arguing. I think there's 3 different hypotheses for case number 3. Daniel was saying that air is heavier, so the balance will be affected, and was saying that it's going to float. The balloon's going to float, so the balance will stay the same. And so Jasper and Daniel are basically having the same hypothesis. They said pretty much the same thing. So those were the various unclear hypotheses, I guess, that the students developed during the course of the lesson. And going on to question number 2.
Did you have the one where that air inside an object is heavier than the air outside? I think I have that.
Yeah, that's it.
They were looking at the balloon and the balance, and what happens to the balloon. What happens to the balance when the balloon is inflated?
Yeah, I know.
What happens to the side where the balloon is? Okay.
I think it's further in the latter part after they had inflated. They had some more hypotheses. Okay, but you can go ahead. Sorry about that. Go ahead, Ashley.
I thought that once they started testing, then that was part of the falsification process. So that they couldn't I guess they could re-hypothesize after falsification.
But did they see that their hypotheses did not hold? Were they able to see that at the end?
Pardon me, did they see what?
I'm asking if they were able to see that the hypotheses that they had initially, that those hypotheses were not supported.
Because it did expand, they were able to see that. I think one person got it right. If I read it correctly, he said it will one side will be heavier than the other, or whatever, something like that. It will not stay the same. So when they did it, they actually proved that one of the hypotheses was correct, if I read it correctly.
Okay, but you notice how they okay. All right, so after they did the experiment, and Daniel was like, how come it came down then, right? Because even after the experiment, and they saw that one side was hanging down, and they were talking about it, and Anne was still saying that the air is light and it would make the balloon float, and then Daniel was like, so how come it came down? It came down then, So they were still, I think they were still unclear. I mean, although
I think Daniel was arguing with Anne, because Anne is like, she went on to say, I don't know, I thought I'd just stay the same with whatever I was arguing before. So Daniel was still trying to explain the hypothesis to Anne.
Okay, so Daniel seems to be the one who was clear. Right? From the beginning, I thought Daniel was the one who was clear, right? But but even at the end, Joanne says that it was gravity that was pulling it down, pulling the air down. So I think she was discounting the whole fact that there were that you had different masses on the two sides. So in terms of the air being contained in the balloon and that making it heavier than the other side, I don't think that that she really understood actually what was happening at all.
Right.
Yeah. Okay. The limitations then of falsification.
Based on the lesson.
Yeah.
I guess you can say that if there's no clear consensus on the hypotheses, then there can be some difficulties in proving falsification if you didn't have a clear hypothesis.
That's true. Yeah, that's true.
Sorry, I think they let the Yes, they let the preconceived notions that they had come into play, even though they was actually seeing it. The perception of what actually is was not kind of meshing with what the fact was, so they were still a bit confused.
So yeah. So those preconceived ideas that they also brought to their interpretation was incorrect as well. And one other limitation that I see, because remember that one of the things that falsification assumes that if you get a piece of evidence that conflicts with, you know, the current theory, that you're just going to change your mind about it. And I think that is a limitation, because falsification is assuming that people will very readily give up their misconceptions and their prior beliefs and ideas. And that's not necessarily so, as we can see here, right? So some of the students still had the beliefs that they had at the beginning, even though they had carried out the experiment and the experiment had worked in the way that it was expected to work, right? So that is one of the things, that was one of the criticisms actually of falsification, that nobody really sets out, no scientist, no person really sets out to falsify their own idea. You know, people tend to hold on to their ideas rather than giving them up very, very, you know, readily. All right, anything else? Anybody else on that? Want to add anything? No? All right, I think you guys are pooped now. All right. I want to thank you all for being here today, and I want to thank you for your participation. We are halfway through, so kudos to you guys. You're doing well. Please remember your assignment for tomorrow. All right, so just email those to me. And next week, starting on, well, I'll have the container up for Monday. So as of next week, we'll be able to use our course container on OURVLE. I also, for next week, you'll also have some readings to do, which I'm going to send to you. So each person is going to do a reading, a short reading, and share. It's going to be individually. Each person will share what they have read and, you know, talk about it. Oh yes, and I'm going to grade those. That's like 5%. All right, so it's a little presentation. So you're going to spend a little bit of time on it. Also, I am going to send you the second assignment. So now that you've finished the first one, I'll wait until tomorrow because I don't want you to get overloaded. So when you've submitted the first one tomorrow, I will send you the second one. And about Thursday next week, we will have, remember, we have a test that we're going to do. It's going to be like an hour, right? And it's going to be based on this unit, induction and falsification. So we'll talk a little bit more about it on Tuesday.
When is the test?
I think Thursday might be a safe day for it. Unless you want it on Tuesday.
When is the next assignment due?
The next assignment is going to be due like next week, Friday.
Really?
So can we have the test the following week?
If we might run into some issues because there are 3 assignments. So if it is the following week, that is going to be week 4, which is going to have its own set of assignments and stuff. So we might have some challenges there if we do that.
Oh, there's definitely going to be challenges regardless.
Yeah, I just mean in terms of us running out of time. All right, tell you what, why don't we look at the assignment on Tuesday, and if you still think it is going to be something that you're going to need additional time for, because I don't really think so, but on Tuesday we can talk about it a little bit, and then if you think it is something that you're going to need more time for, then we'll discuss it.
Okay.
Right. And
I didn't see a test on the course outline. Is that I thought we were just, assessment was just assignment based.
Yeah, it's not a test per se, it's a case, right? So I mean, it depends on how you look at it. So it's a case, You read it in class. So you can use all your material, etc. Right? Well, no, you can't really use your material. No. All right.
Yes, we could. Don't worry.
No, you can't. You won't have time. You won't have time for that. It's just right. You won't have time for that. So,
Samuel.
Yes, Samuel.
Yes, the test you're talking about, are we going to do it wherever we are, or we have to go to the university's open center to do the test?
I had thought of you going to the center, but I think I'm going to allow you to do it where you are, but then you have to upload it immediately to me for me to see it. Yeah, I think I'll go with that. Yeah, because we were kind of thinking about what are the different possibilities for getting it done. So what you do, you'll have to just probably type it straight and then upload it. So I'll probably have to give you a little bit more time than I normally would for that. Question?
Okay, thank you.
All right.
What if we write it out by hand and scan it or something like that? Just if someone maybe not, like, or will we have enough time? I mean, some people may not be able to type as fast and stuff.
Okay, all right. Then you could do that. You have but then you would need to have a scanner where you are.
Right.
Okay. Well, you could do that if you have that access. So you.
Okay.
Mm-hmm. All right, so what I want you to do then, all right, because I figure people you're thinking about it. So think about it, and we'll talk about it first thing at the beginning of our class on Tuesday. I may ask you to change a class time as well. That's next week, Thursday. I'm going to send you an email with the suggestions, because I'm going to have to spend a little time thinking about it. So I'm going to send some things that I'm suggesting, and you tell me if you can fit in to any sort of changes or what might work for you. All right?
The class time from the morning, different from the morning?
For the Thursday.
Okay then.
Yeah, but just for that day.
Just a one Thursday, just one.
Yeah.
That'll be. You want to be later?
I'd prefer if it were later, or if we can kind of break it up into earlier and then later. The thing is, in between the class, there is something that I need to do, an appointment that I have. So I'm going to look at it and make some suggestions, and then you tell me which one works for you guys, or if none works, well, fine, right? We can try to see how we can work around it.
Okay, because I'm at work to come back. I have to come from work to get here for 10:30, and I have to break up and then go back and come back. It might be a bit difficult for me. But if it's in the evening, like maybe after 4, that'll be good for me. That's fine. Thursday. That's okay.
You mean after 4 your time?
Yes.
Okay.
If that's I I can come directly after school dismisses. I can do that. But I normally have to report to work for signing and then come back to reach to 10:30. Because you're at work, government time.
Yeah. So. Okay. Is the possibility of a Friday class? Is a Friday meeting a possibility?
Samuel Dominica.
Yes, Samuel.
This Friday or next week Friday?
Next week. We're talking of next week.
Okay, no. It will be very difficult for me because school will be closing next week Friday.
Okay. All right.
Very difficult. Next week Friday, because that's when the school closes here in Dominica.
Okay. All right. All right. Let me put some ideas on the table, and then you can look at them. All right.
Okay, we'll do that. Okay.
All right. So everybody, thank you again, and have a good weekend.
You too.
All right. Expect my mails. All right.
Okay.
All right. So let me take the time. Okay.
Thank you.
Bye,
Thank
Ashley.
you. Bye. Have a good
Bye.
weekend.
Bye, Jason. Take care. Bye, Samuel. Bye, Linton.
Okay, bye.
Bye.
Bye, Sandro.
Bye.
Yeah, bye, Ava. Bye,
Bye-bye.
Vanessa and Tracy.
Bye.
All right, take care. And I'm sure Vanessa has said bye. All right, take care.